Hello. So for this video, we will be talking about a dilution problem. Okay. When we say dilution problem, this refers to, so this will be the model scenario, okay, of a dilution problem, right? So say we have a tank, okay, and then for a tank, there will be a solution going in, right? Okay, and then there will be solution going out. So this will be our model scenario for a dilution problem. Okay. So this is I'm referring to it as a model scenario because we can apply this to other situations as well. Okay. Basically, if a mixture is involved, okay, this can be uh, used, okay, to analyze that system. Now, what happens here is, say we have a amount of, okay, so for the following sample problem, so we'll be talking about brine solution, okay, brine solution. When we say brine solution, that is saltwater solution, okay, so salt plus water, right? So what happens here is, say in going in to the tank, okay, we will have a solution. Call this one solution in, okay, and then we have solution out. So if there is, say, inside the tank there is an amount of salt, okay, and you want to increase the amount of salt, okay, now if you will close this valve, and uh and we introduce a new solution, especially if the tank is, say, already almost full, right? Then you increase the solution, so the level inside the tank will increase until it is full. Now when the tank is full, and it is not yet the concentration that we want, okay, so uh we need to flush out some of the solution, okay, so that we can change the mixture, okay. Now this is not only applicable to brine solutions. As I've mentioned, this is just our model. For example, we have alcohol, we have 70% in the commercial setting, we have 70% alcohol, we have 40% alcohol. Now to change the concentration from, say, 100% alcohol, we need to introduce water, okay. So if you want it to be 70% uh, water, then we introduce alcohol, 70% of the volume as alcohol, then 30% water. Now if you want to make it 40%, okay, and then the tank is already full, we can flush out some of the solution and introduce more water, so that after some time, okay, what will be left is 40% of the alcohol and then 60% of water. Now we have a 40% alcohol solution, so something like that, okay. Now in the formula for a solution problem or dilution problem, mixture problem, okay, what we have here is the amount of, again, we will use salt as the model, so the amount of salt inside is, okay, depends on the rate of the salt going in, okay, salt rate in minus salt rate out. In other words, if we will introduce a solution with more salt than what is going out, then the mixture will have more salt inside, Okay, now if we introduce a solution with less salt going in, so more salt will be going out. So that will make the overall salt inside the solution less. Okay, so this will be our main formula going forward. Okay, or we can just remove the salt to make this formula accommodate to any possible scenarios or to all possible scenarios. Okay, so the overall rate of change of our mixture will depend on the rate going in and then the rate going out. Okay, now let's go to our sample problem. So here, a tank initially holds 100 gallons of brine. Okay, a tank initially holds 100 gallons of brine solution containing 20 pounds of salt. Okay, so at time 0, fresh water is poured into the tank at the rate of 5 gallons per minute, while the well-stirred mixture leaves the tank at the same rate. So find the amount of salt in the tank at any time t. Okay, so according to our problem, so there is also a mixture uh, mechanism here inside the tank. Okay, to make sure that the mixture inside the tank is always uniform. Now, where can we find this scenario? We will always find this scenario inside any manufacturing plant, which maybe the product is liquid or maybe this is a liquid that is needed for any process. So the liquid should be mixed thoroughly to make sure that the solution is homogeneous. Now, as per our formula, so the amount in this case is salt, right? Is rate in minus rate out. Rate in minus rate out. Now think of this, okay? So for the unit of rate, rate in minus rate out. In our example, that will be pounds of salt. Okay, so that will be the amount of salt all over time. In this case, minutes. Okay, so pound of salt in minutes. Hopefully you follow that one. Now, we want to find some, to call this one, we want to find some parameters here that when combined will have this unit, okay, pounds of salt per minutes, right? Now, if we look at our uh, givens, okay, say on the going in side, okay, or solution in uh, part of our given. So here we have fresh water poured into. Okay, so this one is going in at the rate of 5 gallons per minute. Okay, so 5 gallons per minute, right? And then our solution, okay, let's go back here to our drawing. So our solution will have a rate, okay, or rather will have fluid flowing in the rate of say volume per time. Okay, volume per time. So in the case of our example, gallons per minute. That's how uh, the solution is going in or going out of the system. Okay. Now, other examples of volume over time, we say uh, liters per minute, liters per second, okay, liters per hour, etc., etc. In this problem, gallons per minute, okay. So volume of the fluid over time going in. Now the concentration of our, say, salt in this case will be the amount of salt. Okay, the amount of salt is called that Q. Okay, now the amount of salt is in mass, is a mass, right? Let's call that M over the volume. Okay, so say I have 5 kilograms of salt in 10 liters of water. That's my salt concentration. So this is mass over volume. And then for my fluid, okay, for the flow of the fluid, say I have 1 liter per minute. Okay, so this is our volume over time. Now notice that if we multiply this 2, okay, so M over V times V over T, this will cancel out. Okay, so we will be left with M over T, which is the mass of our substance, in this case salt, divided by time. Okay, or the rate of the substance. Okay, so this is our formula for the inside going in side of the solution, and then for our going out side of the solution. Okay, now this one we will refer to this as, since this is mass over volume, we will refer to this as the concentration. Okay, we'll refer to this as the concentration, and then this side we will refer to this as the flow rate. In other words, our rate in, okay, is concentration in, sorry, concentration in times flow rate in, then minus by concentration out times flow rate out. So this will be our basic principle for brine solution. Okay, now for brine solution, I suggest that we will approach this on the differential level. We will not go with the basic formula or the derived formula as the first step. I suggest that the first step always is the DE one. Okay, because later when, okay, so let's try to write the given for now so that you can see. So a tank initially holds 100 gallons of brine solution, okay, containing 20 pounds of salt. Okay, so at time 0, fresh water is poured into the tank at the rate of 5 gallons per minute. So this is the flow rate in. Okay, so flow rate in is 5 gallons per minute. And then, what is going into our solution? Fresh water. What does fresh water means? Fresh water means there is no salt. Okay, so since there is no salt, the concentration going in is 0. Okay? Now, if there is a salt going in, so we will have a value here now. Concentration going out. Of course, the concentration of the salt water solution going out of the mixture will depend on the current amount of salt. So since the current amount of salt changes, we cannot say or we cannot point out a very an instantaneous concentration for now. Okay, so we will call this one, back to our formula here, mass of the salt divided by its volume. Okay, so for the concentration going out, this will be the concentration inside the tank, okay, or the concentration of the current solution. In other words, that will be the amount of salt, which we don't know the value, okay, instantaneous value, divided by the volume of the tank. So we will write here the whole volume of the tank. Okay, so here a tank initially holds 100 gallons of brine solution. So this is the, okay, this is the volume of the tank. So Q over 100. Okay, so I hope we follow that one. Then the flow rate is while the well-stirred mixture leaves the tank at the same rate. Okay, so say it says here same rate as the flow rate in. So this will be times 5, okay, gallons per minute to 100 gallons. Okay, so this will be our formula for now. Again, dq over dt is equals to concentration in 0 because it is fresh water, flow rate in 5 gallons per minute, minus concentration out, Q, okay, the amount of salt at any given time, divided by the volume of the tank, in this case 100 gallons, times flow rate going out, which is 5 gallons per minute. So the gallons will cancel. Okay, then this one is 0. This one is 0. So 0 times 5 is 0. Okay, so we will be left with dq over dt is equals to negative 5q over 100. Okay, you will notice if what you're doing is right or wrong, because uh, if you're introducing fresh water to the solution, meaning the amount of salt inside the mixture will decrease. So since it will decrease, the amount of change would be negative. Okay, now if we are introducing salt, or we are introducing more salt than going out, meaning the amount of salt should be more or increasing. So the change of rate should be positive. Okay, so that's one of our context clues if what we're doing is right or not. Okay, resuming, notice that this is a variable separable solution. Okay, so let's try to solve this one. So dq over q, okay, is equals to negative 5 over 100. So negative 5 over 100, we can simplify this one as, so negative 5 over 100 is 1 over 20. Okay, so dq over q is equals to negative 1 over 20 dt. Then we can integrate both sides. We will have ln of q is equals to negative t over 20 plus c. Okay, using this as base or as exponents of e to eliminate e, we will have q is equals to c1 e raised to negative t over 20. Okay, so this will be our working solution. And then for our given, we have initially the solution contains 20 pounds of salt. Okay, meaning at time 0, okay, so at time 0, the amount of salt is 20 pounds. Not time 0, sorry. 20 is equals to c1 e raised to negative 0 over 20. So this one will be e raised to 0 or 1. So therefore C1 is equals to 20. Okay, so we can write this to our equation. So Q now is equals to 20 e raised to negative t over 20. Okay, so this will be our final answer. Again, the unit here will be pounds, based on the problem. Right, so that's it for our first problem on the mixture dilution brine problem. Okay, uh, now I want, before we proceed to the next example or next video, I would like to emphasize this one. If we have a concentration of salt going in, this one has a value. Okay, if this one has a value, this will no longer be a variable separable equation. Okay, so that's why I suggest when going in to a mixture problem, we start with the differential equation first before we proceed with the solution. Okay, we will I really suggest that you start with the differential equation first and not the what do you call this one, not the derived equation. Okay, so see you on the next video.